Welcome everyone to our fifth module for CCNA Routing and Switching Curriculum Scaling Networks version 6.0. Again, my name is Lee Pineda. Okay, for this week, we're going to talk about the one out of two dynamic routing protocol that was covered from module number 4. Alright, so in that past module, okay, that is the title of that module is dynamic routing. So we found out that dynamic routing protocols are used by routers to facilitate exchange of routing information between routers. Also, we learned that the purpose of dynamic routing protocols includes the discovery of networks, remote networks that is, maintaining up-to-date routing information, how they choose the best path to destination networks, and of course the ability to find a new best path if the current path is no longer available. Okay, so for this week, as I've mentioned, we're gonna talk about the first out of two dynamic routing protocols. Okay, we're gonna discuss how it works, okay, its operation, and of course its implementation on both IPv4 and IPv6 network. Okay, so without further ado, let's move on and take a look at this week's objective. So now let's take a look at this module's objectives. First, we're going to talk about EIGRP characteristic, wherein we're going to explain the features and how EIGRP behaves. We are also going to describe the basic features of EIGRP along with the different types of packets used to establish and maintain an EIGRP neighbor adjacency. Before the end of this module, we're gonna learn how to implement EIGRP for IPv4. We're gonna have a sample configuration topology using Cisco Packet Tracer to do that, and also to configure, okay, EIGRP, the proper configuration of this dynamic routing protocol for IPv4 and a small routed network. Okay, of course, after the configuration, you will need to verify if EIGRP actually works, okay, by using differential commands, okay, that is applicable to check and to troubleshoot EIGRP setup. Okay, on the last part of this module, okay, we're gonna also try and implement EIGRP for IPv6. Okay, so that is two different type of implementation. Okay, one for IPv4 topology. The other one is the implementation of EIGRP for IPv6 network. Okay, afterwards, we're going to compare characteristics and operation of both EIGRP for IPv4 to EIGRP for IPv6. Okay, then as I mentioned a while ago, the proper configuration of this dynamic routing protocol in a small routed IPv6 network. Okay, so same with IPv4, we also have different verification commands in order to check if your IPv6 implementation is also working well. Okay, so those are the important objectives for this module. Okay, let's start off with our discussion. Let us start by looking at the characteristics of EIGRP. Okay, so as we all know, EIGRP stands for Enhanced Interior Gateway Routing Protocol. It is an advanced distance vector routing protocol developed by Cisco Systems. As the name suggests, right, EIGRP is an enhancement. Okay, this was discussed from previous module. No, we found out that EIGRP is an enhancement of another routing, Cisco routing protocol, which is called the IGRP, or Interior Gateway Routing Protocol. Okay, we also discussed the differences between the two. Okay, we found out that IGRP is an older version, classful type, okay, which is already obsolete since iOS 12.3. Okay, now the enhanced version of IGRP is the EIGRP. This was created as a classless version of that old dynamic routing protocol. Okay, so since it is classless, it is an ideal choice for large multi-protocol networks built primarily on Cisco routers. Okay, so even though this dynamic routing protocol is a Cisco proprietary protocol, in 2013, Cisco released the basic functionality of the EIGRP as an open standard, no, to the IETF. Okay, so what does that mean? Okay, this means that other networking vendors, okay, whether they are Cisco product or non-Cisco product, can now implement EIGRP on their equipment, okay, to interoperate with both Cisco and non-Cisco routers. Okay, so it means that it is already a cross-platform type of protocol. Okay, as early as 2013. Okay, all right. So aside from that, EIGRP is also known to include features of both link state and distance vector routing protocols. Okay, again, no, those terms, okay, was discussed from module 4. Okay, what is the difference between link state and distance vector routing protocol? Right, so EIGRP includes both of those features. Okay, so take note of that. However, EIGRP is still based on the key distance vector routing protocol principle. So though it is accepted that it has both the link state and distance vector capability, EIGRP is still considered, mostly considered as a distance vector type of routing protocol. Okay, so it means that the information about the rest of the network is learned from directly connected neighbors. Okay, so with that being said, so here are the different EIGRP features along with its description. Okay, so number one, EIGRP uses what we call as the dual algorithm or diffusing update algorithm. Okay, so this is the algorithm that is used whenever you implement EIGRP. Okay, using this algorithm, all right, EIGRP stores all available backup routes for destination so that it can quickly adapt to alternate routes when necessary. That actually what makes EIGRP, all right, contain both link state and distance vector type of routing protocol. Okay, because of this algorithm. Okay, the next feature is the establishment of neighbor adjacencies. Okay, so EIGRP establishes relationships with directly connected routers that are also enabled for EIGRP. Okay, so in later on we will be introduced with the proper syntax. Okay, using the correct code. Okay, so that EIGRP can do this one. Okay, so we have certain parameters to set up. Okay, in order for this protocol to establish a relationship with its neighboring EIGRP routers. Next, reliable transport protocol. Okay, or what we also know as the EIGRP RTP. Okay, so this is the one that provides delivery of EIGRP packets to neighbors. Okay, so both RTP and neighbor adjacencies are used by the dual algorithm that is being implemented by uh, this routing protocol. Next, partial and bounded updates. Okay, partial and bounded updates. Now, unlike RIP, unlike RIP, EIGRP does not send periodic updates. Okay, um, the term partial means that the update only includes information about the route uh, that usually changed. Okay, so that's why it is considered as a it is also considered as a link state type, right? So because we learned that in a link state type of routing protocol, no, a certain dynamic routing protocol only sends routing update whenever there's a change on the network. Okay, it's not periodic type, unlike RIP or the old IGRP. Okay, now the term bounded updates refers to the propagation of partial updates that are sent only to those routers that the the network change effect. Okay, so the advantage of that is we can minimize the bandwidth that is required to send EIGRP updates. Okay, the last one is equal and unequal cost load balancing. All right, so it supports both equal and unequal cost load balancing. This is usually an advantage that makes it flexible, that allows network administrator to better distribute traffic flow in their networks by actually tweaking um, a certain parameter in terms of its metric. Okay, later on we're gonna try and do that. Okay, so these are the different features, okay, of this dynamic routing protocol. All right, so let's move on with the next slide. Okay, so moving on, let's now take a look at the different EIGRP packet types. Now, IP-EIGRP relies on 5 types of packets to maintain its various tables and establish complex relationships with neighbor routers. They are namely the hello packet, the update, acknowledgement, query, and reply. Alright, so we're going to discuss each of these packet types on the next slide. Okay, but be aware that EIGRP uses 5 of these different packet types. Okay, some of which are used in pairs. Alright, then the EIGRP packets are sent using either RTP reliable. Okay, take note of that. So RTP reliable or unreliable delivery, and can be sent either unicast, multicast, or sometimes both. Okay, so again, that's hello, update, acknowledgement, query, and reply. Okay, so let's take a look at the hello packets first. Alright, so hello packets are used for neighbor discovery and to maintain a network adjacencies. So they are sent with unreliable delivery and sent on a multicast default IPv4 address 224.0.0.10. Okay, they are also sent multicast on most network types. Alright, so upon hearing hello packets, a router creates a neighbor table, and the continued receipt of hellos maintains that table. So the graph here shows the default values in terms of the default hello interval, okay, according to bandwidth. So for example, let's say the bandwidth is around 1.54 MB. Okay, so the default hello interval is around 60 seconds. So the router are sending hello packets once every 60 seconds. Okay, along with the default hold time. Okay, now if the bandwidth is greater than 1.54 Mbps, so faster bandwidth means it has lesser default hello interval. So as you can see right here, it is only around 5 seconds. That is on, for example, on the T1 and Ethernet network. Okay, so another thing that you need to remember is that hello packets are always sent unreliably. Okay, unreliably. So as we learned in CCNA1, whenever you send a packet unreliably, okay, you don't expect an acknowledgement. Okay, so same with hello packets. So the routers send hello packets, and then they do not require acknowledgement. So they just flood the neighbor routers with hello packets, okay, with a given time interval, okay, to check, okay, and to create a neighbor table on that particular router whenever they hear those hello packets. Okay, so again, no, the default. Okay, kindly take note, the EIGRP multicast IPv4 address. So they're using this default 224.0.0.10 address to send hello multicast EIGRP packet, hello packet. Okay, for IPv6, it is FF02::A. Okay, next. So the next type of packet is the EIGRP update packet. Okay, so this one is used to propagate routing information to EIGRP neighbors. Okay, again, so in contrast with hello packets, okay, this time update packets are sent with reliable delivery, whether unicast or multicast. Okay, so I said that again, update packets are sent reliably. Okay, so they are used to propagate routing info to and from a particular router that is part of the EIGRP routing update. Alright, so it is sent initially to exchange topology information or whenever there is a topology change. Okay, so EIGRP updates also contains needed routing info and are unicast to routers that require it. Okay, that's why at the start of this module, I mentioned that EIGRP somewhat works like a link state type. All right, so it is considered as both link state and distance vector in a sense, no? Because it only updates packets reliably, no? To routers that needed information or the routers that requires that information because there's a change in their particular network. All right, so this is the update packet next to the hello packet. All right, so after the update packet, okay, the next thing that the routers will send is the acknowledgement packets. All right, so as I said a while ago, update packets are sent reliably, so they will wait for an acknowledgement. Okay, the characteristic of acknowledgement packets are they are dataless. Okay, as you mentioned here. So hello packets used to indicate receipt of any EIGR packet using a reliable exchange. Okay, those are acknowledgement packets. And also, they are used to acknowledge the receipt of update packets along with query and reply packets. So we're going to talk about the remaining packets, type of packets later, no? Namely query and reply. Okay, after acknowledgement, okay, whenever there's need for a checking of a network, so a query and reply packets are used, okay, by the EIGRP algorithm, particularly when searching for network. So from the term query, right? So query, all right, if they request for specific information from a neighbor router, all right. So after the query, okay, but take note, no, they both of these packet types use reliable delivery and therefore require acknowledgement. Okay, so Queries, on the other hand, can use either multicast or unicast, whereas replies are always sent as unicast. Of course, no? Query is like a broadcast. Okay, so it can take a form of multicast or unicast. You can query, for example, let's say R1 is sending query to R2 and R3, so that is multicast. Okay, but in terms of reply packet, okay, of course, there's only specific packet for that particular router. Okay, that's why replies are always sent as unicast. Unicast means 1:1. Okay, as we learned in from CCNA 1. All right, so these are the different types of EIGRP packets. Okay, so just take note of these terms, so they might pop up with our instructor's exam or quiz right after each module. Okay, so with that, let's move on with the implementation process, the configuration process. First, of EIGRP for IPv4 network topology. Okay, so we're gonna use this sample topology shown in the screen. Okay, so as you can see, this topology displays a network. I actually pulled it from this chapter so that we can have um, a dummy topology that we can work the EIGRP with. Okay, now the routers in this topology have already starting configuration. No? If you're going to observe, okay, all the IP addresses are already in place. Okay, particularly on the interfaces of the routers. Okay, however, there's no currently static routing or any dynamic routing configured on any of the routers. Okay, so I'm gonna transfer this to our in a packet tracer format so that we can have the actual simulation and show you the addresses that are already fixed, okay, per interface. Okay, so that we can focus mainly with the configuration of IPv4 EIGRP for IPv4 topology. Alright, so we are now inside Packet Tracer, and then we're going to use this sample topology to try and run EIGRP routing process. Okay, so as you can see in this topology, this is an IPv4 network. We have 3 router setup, and the following task to complete this or to converge the topology are as follows. Number 1, we're going to try and enable the EIGRP routing process, IPv4 EIGRP routing process. We're going to enable that per router. Second, we're going to advertise directly connected networks. Alright. Third, we're going to configure passive interfaces. We're going to explain as we move on what are passive interfaces. Next, we're going to disable automatic summarization. And then why do we need to disable that later? After that, after full configuration, of course, you will need to save your config per router and then verify if your EIGRP configuration works by sending end-to-end connectivity ping. Okay, that is pinging computers to and from a network, okay, to see if they can successfully reach each other and to see if our IPv4 topology is already converged with the EIGRP routing protocol applied. Alright, so first up, okay, let's try and check first the initial configuration of each router. So I'm gonna pull on the CLI of R1. I'm gonna enter privilege mode. Then I'm gonna issue the command show run. Okay, so let's try and look at the interfaces. So as I mentioned a while ago, IP addresses for each interface are already pre-configured in this topology, so we don't need to worry about that. So you notice that in G00 of R1, Okay, already have the IP address up and running. Same with S00, the IP address is already up and running. Same with S001, already have the IP address as well. So let's try to look at R2, privilege mode, show run, look at the IP addresses. Okay, so I think it's all good as well. Okay, so we already plotted the IP address that corresponds to the given topology map. R3. Okay, this time I'm gonna use, alright, instead of show run, okay, you can also use show IP interface brief. Okay, you can also use this one to check for the summary of the IP addresses configured for interface. Okay, so it's all green, so it means everything is working well. So all we have to do is to go straight with enabling EIGRP routing process per router. Alright, so let's go ahead and do that. Okay, let's start off with R1. Okay, now to enable EIGRP routing procedure or EIGRP dynamic routing per router, so we need to go to privilege mode and then enter global mode. Alright, so remember this, no? Inside global mode, all you have to do is to type in router space EIGRP, alright, space the autonomous system number or the AS number. Okay, so the syntax will be router space EIGRP space the AS. Okay, now when you say AS, or also known as the autonomous system number, okay, we can use the value from between number 1, okay, to 65,535. So if you're gonna try and check, okay, what is the range of the AS number, so you just put question mark there, and then you have this range right here. So it is from 1 up to 65,535. Okay, now the autonomous system number, it is used for EIG configuration or EIGRP configuration that is locally significant, no, to the EIGRP routing domain. So for example, let's say if we are creating or we are trying to converge this network, then all of these three routers must use, okay, the same autonomous system number. All right. So if we choose, for example, let's say 10, okay, router EIGRP 10 for R1, the same AS number must be configured on the other routers. That is part of the EIGRP network that you are building. Okay, so R2 must have the AS number 10, R3 must have also the same AS number. Okay, so AS functions or autonomous system number functions as a process ID, no, to help routers keep track of multiple running instances of EIGRP. So for example, let's say in R1 only you have multiple EIGRP running, no? So that is being used by router to keep track, all right, of multiple running instances of EIGRP so that they will know which part of the EIGRP routing process they will run with the other paired router or their neighbor router. Okay, so each instance of EIGRP can be configured to support and exchange routing updates for different networks as well. So in this scenario, okay, we're gonna use let's just make it simple. We're just gonna use EIGRP AS number 1. Okay, so I'm gonna configure that on R1, enter. All right, so as you notice, no, once you press enter, your prompt will change to config router. Okay, so I'm gonna go to R2. All right, do that as well. So global mode. All right, router EIGRP. Then I'm gonna use 1, enter. Okay, go to R3 and then do the same procedure. Global. All right, router EIGRP 1. All right, so we already configured, okay, or run the AS number or the enabled, sorry, we already enabled dynamic routing protocol EIGRP with AS number 1 on each router. Now, just take note, now when you issue this command, it does not automatically start the EIGRP process itself. No? The router is not yet, okay, once you issue this, still no, the router does not start sending updates just yet. Okay, it is only a command that provides access to configure the EIGRP settings. That's why your prompt changed to config-router. Now, just in case, for example, no, you wanted to remove EIGRP. All right. Let's say you have mistakenly entered the AS number instead of 1. You mistakenly type 2 or 10. So to totally remove the EIGRP or router EIGRP routing process from a device, we use the no router EIGRP and then the AS number inside global mode. So what does that mean? Okay, you go back to global mode and then you type in no router EIGRP space and then the AS number that you wanted to remove. Okay, so for example, in this case, I'm going to remove 1. All right, so there you go. All right, so these are the initial steps, no, on running router EIGRP on each router. And then later on, we're gonna add more parameters, okay, to get EIGRP dynamic routing protocol running, okay, so that we can achieve network convergence. So let me just return the command. So we removed it, router EIGRP, then autonomous system number 1. Okay. Okay, so before moving on with the completion of EIGRP configuration on our 3 routers, okay, let's have a subtopic first. Okay, this time we're gonna look at the EIGRP router ID. Okay, so whenever you run EIGRP dynamic routing protocol, okay, router IDs or EIGRP router IDs are used, no, between routers to uniquely identify each of them in the EIGRP routing domain. Okay, now we have a procedure, okay, on how to configure the router ID. So let's say, for example, if a network admin decides to manually put router IDs on each router, okay, so the command will be, okay, you're gonna use the command EIGRP space router dash ID, and then space, and then you're going to follow the IPv4 address router config command. Okay, or the router ID must be written in an IPv4 address format. Okay, I repeat, no, that is EIGRP router dash ID, and then whatever you want to assign router ID on that router, okay, in an IPv4 address router or in an IPv4 address format. So, for example, let's say 1.1.1.1 or 2.2.2.2, as long as it is in an IPv4 address format. Okay, now that is the on top of the hierarchy, a manual configuration of router ID using EIGRP router command. Now, if, for example, let's say a network administrator did not configure a router ID, okay, routers within themselves, okay, will choose the highest or will choose a certain value to be used as their router ID. So in that case, it's going to be the highest IPv4 address that is configured on any of its interface, or sorry, or of any of its first loopback interfaces. Okay, loopback. Okay, I believe we used loopback in CCNA1 before and CCNA2. No, loopback addresses does not shut down. Okay. Okay, in fact, it is a virtual interface. that is automatically in the up state when configured. So for example, let's say in R1, you configured an interface loopback address of 10.10.10.3. Alright? Um, that virtual interface will automatically be in the up state. Okay? And the interface does not need to be enabled for EIGRP. Okay, so sometimes loopback addresses are just used to test the network, or for example, let's say you're going to use that virtual interface for a certain ping reply or ping request. Okay, so that's how loopback address works, or loopback interfaces work. So if there's any loopback address configured on a particular router, okay, the highest configured IPv4 loopback address will be considered as its router ID. Okay, last consideration. Number 3, if no loopback interfaces are configured, then the router will choose the highest active IPv4 address of any of its physical interface. So for example, let's say in R1, look at this, now R1. Okay, let's assume that there's no manually configured router ID on this router. Okay, there is also no loopback address or loopback interface configured. Okay, so 1 and 2 are off the list already. No, so the question is, what router ID will R1 use in terms of EIGRP identification? Okay, so the last option here says that it will choose the highest IPv4 address of any of its physical interface that is configured on that particular router. So this R1 will compare, no? For example, S00, what is the physical IPv4 address? That is 172.168.1. L001 is 192.168.10.5. Okay, G00 is 172.16.1.1. So R1 will retrieve those three values and then compare which among those values is the highest. And then it will choose the highest active IP address. That's why, as you can see right here, R1's router ID, okay, it uses the 192.168.10.5 because that is the highest IP address compared with 172.16.30 and 3.1 and 172.16.1.1. Okay, so that will be the router ID of R1. So same instance with R2, you notice, no? So gathering all the physical addresses, okay, active physical addresses of this router R2, and then you will notice that the highest amongst those IPv4 addresses is the 209.165. So it consider that as its router ID. Okay, for R3, it will use the 192.168.10.10. Alright, so the options are 10.6, 10.1, 10.8, alright, and 10.10. So obviously 10.10 is higher or highest amongst those configured IPv4 address on that particular interface. That's why it was elected as its router ID. Okay, so again, no, the hierarchy, no, that we follow, whenever there is a manually configured router ID. So for example, let me show you on the next slide. Look at this. Okay, so let's say we're going to manually configure R1 with router ID 1.1.1.1. All right, and then given all the physical addresses, they are 172.192.168.10.5 and the rest. Okay, so even if, okay, the physical addresses are higher than the manually assigned router ID, which is only 1.1.1.1, still from the hierarchy on which router ID will the router pick. Okay, so the manual configuration of router ID is on top. Okay, so it will disregard the rest of the options as long as there is a manually configured router ID. So in this case, the router ID of R1, as you can see right here, let me zoom that. okay, is 1.1.1.1, the one that was configured on the EIP router ID, router-ID command. Alright, so that one right there. So again, no, as I've mentioned, okay, even if there are higher values, okay, 192, 172, 172, these are higher values compared with 1.1. Not to confuse, no? Still, routers will prioritize, okay, what was manually configured through this EIGRP router-ID command. Okay, so if it will only choose the highest IP address when the EIGRP router ID is not configured manually. Okay, in fact, after the router ID check, okay, it will need to check first for the loopback, right? So the loopback interface first. Okay, before the IPv4, the highest IPv4 address. So it has to go through this two steps procedure of checking first before it can finally decide on the IPv4 address. So if none of these first two options are present, then that is the time that it will choose an IPv4 address, the highest IPv4 address. Okay, so same scenario with R2. So we configure 2.2.2 here. So that would be the router ID for R2. Now, in case for the packet tracer files that you're going to submit, okay, if there is a requirement for you to change the router ID, then this will be the command. So we configure it inside EIGRP. All right. So once you entered the router EIGRP command along with the autonomous system number, all right, inside EIGRP command for the config router prompt, that is where we set the router ID. Okay. Oh, and one last thing, by the way, the command for you to check, okay, the router ID of a particular router or what router ID did that router choose. Okay, so the command will be, okay, look at this. It's going to be show IP protocols. Okay, so when you issue show IP protocols, just try to browse through the middle and then you will see it right here. Alright, so again, show IP protocols. Okay, so going back to our topology. Okay, so we already finished with the enabling of EIGRP routing process. So we are now on the second task, which is to advertise directly connected networks. Okay, so in that case, we're going to use another command. Okay, I believe we used this command already with RIP and RIP version 2. Okay, the network command. Okay, so that is used. The network command is used to advertise directly connected networks or to declare directly connected networks on a particular router and put it inside EIGRP routing table. Okay, so the network command also enables any interface on a particular router that matches the network address in the network router configuration mode to send and receive EIGRP updates. Okay, so the network of the interface is also included, okay, whenever you have an EIGRP routing update. Okay, so let's start off with that command. So all we have to do is to declare, we're gonna declare all directly connected networks from R1. Okay, so let's try to look at that, Okay, if you're going to focus on R1, and then if you're asked how many directly connected networks do you have? Directly connected networks are the networks that has physical connection with R1. So obviously we have 1. Okay, we also have this one, 2. And then this one you have 3. So these are 3 directly connected networks to R1. So what we're going to do is to declare these 3 networks inside EIGRP routing command using the network command. Okay, so we're gonna enter router EIGRP with the correct ES number first, and then inside we're gonna declare these three directly connected networks. Okay, the process is pretty much the same with RIP. Okay, but this time it will in EIGRP we're gonna add a certain parameter, which is the wildcard mask. Okay, we're gonna discuss wildcard mask later as we move on. Okay, so let's start off first with that. Okay, so I'm gonna go to R1. All right, and then okay, proceed directly to global configuration mode. Okay, so let me just zoom that. Okay, so that you can see it clearer. All right, so under global configuration mode, I'm just gonna go back to our EIGRP AS number. Okay, so router space EIGRP1. Okay, so if you have, for example, let's say, if you want to assign the router ID on this particular router, okay, you do it also inside this prompt. So for example, let's say EIGRP router ID, I'm gonna put it 1.1.1.1. Okay, enter. Okay, that is just a supplementary command from our discussion a while ago, but our purpose here is to declare the directly connected network. So I'm going to use the command network, okay, and then I'm going to look at the directly connected networks, okay, on this router. So I'm going to start off with 172.16.1.0 slash the prefix is 24, right? So I'm just going to type in 172.16 dot. All right, you have 1.0 space. Okay, but this time you're not gonna enter. The requirement is actually, if we're gonna put question mark here. All right, the next requirement is gonna be the one that I mentioned a while ago. It will ask for the EIGRP wildcard bits or bits of that particular network address. Okay, now a wildcard mask is an exact opposite or the exact opposite of subnet mask, guys. No. So, for example, let's say I think we already discussed this one in CCNA1. No? In getting the wildcard mask, it's just pretty much straightforward and very simple because all you have to do is to get the opposite of the subnet mask. Okay, get the opposite of the subnet mask. So, for example, let's say the subnet mask for this network is /24, right? /24. All right. So, let me just open my notepad here. Okay, so if /24, the subnet mask will be 255.255.255.0, right? So this will be the subnet mask. Okay, to get the wildcard mask, okay, all you have to do is to invert. Okay, we're gonna invert the value of the subnet mask. Invert means you're gonna get the exact opposite, or put everything to once and then deduct the value from the subnet mask. Okay, but just to make it just to refresh your memory, on how to just to refresh your memory on how to get the wildcard mask, it's just complete opposite of the subnet. So if the subnet is 255.255.0, the maximum is always 255 in an IPv4 address. So the exact opposite will be 0, 0. So that is 0 minus 255. Okay, that gives you, or 255 minus 0, that gives you 255. Alright, so this one matches that fourth octet, this one matches the third octet. Alright, this one matches the second octet, and this one is from first octet. So the wildcard mask for /24 is going to be 000.255. Okay, so let's apply that, okay, on this configuration to complete the network command. So it's going to be 000. Okay, so just press enter. So that would be my first network declaration, okay, that added this network address here. Okay, next I'm gonna add the other network, the 192.168.10.4 network. Alright, so what I'm gonna do is type in network 192.168.10.4 space, Okay, don't forget the space before in between the network address and the wildcard mask. All right. So this time, okay, we're gonna get the wildcard mask of slash 30. Okay, or wildcard bits of slash 30. So to do that, okay, I'm just gonna go back to my short sample here. So slash 30, first we need to get the subnet mask. What is the subnet mask for slash 30? So it is 255.255.255 dot, okay, 252. Correct. All right. All right. So this is the subnet mask. So to get the wildcard mask, we're just gonna get the exact opposite of that number. So it's gonna be 0, 0, 0, 252, 255 minus 252. That only gives you dot 3. Correct. All right. So dot 3. All right. So 255 minus 252, that gives you 0, 0, 0 dot 3. So we're just gonna add that to our configuration here. So we have 0, 0, 0 dot 3. Okay, that is a network declaration for to complete the syntax. Next, okay, finally or last for R1, okay, we're gonna declare also 172.16.3.0 because that is also a directly connected network to R1. Okay, so again slash 30, that gives you point or dot 3. So I'm gonna type in again network 172.16.3.0, then 00.3. Okay, so enter. All right, so that completes the network declaration or directly connected network declaration to R1, and then we already added this network inside EIGRP to be part of its routing update. Okay, to be part of R1's routing update. So when R1 sends now an update to other routers, that is R2 and R3, okay, part of that update already includes this network declaration. Okay, so that is for R1. Okay, so all you have to do is to move on and continue the same process for the remaining routers. Okay, so I'm gonna go to this time. I'm gonna go to R2. All right, so inside R2, so same procedure, global node. Okay, router EIGRP. Okay, 1, autonomous system number 1. Okay, and then let's try to configure router ID also on this router. Let me just resize this one. Okay, so the router ID I'm going to put is 2.2.2.2. Okay, enter. And then I'm going to start declaring the directly connected networks as well. So the command network 172, I'm going to start off with the 172.16.2.0 network. 16.2.0 network. The subnet mask /24, so I'm not going to use the scribble. So by now you should be familiar on how to invert subnet mask. So it's going to be 000.255. Okay, enter. I'm going to declare the other network, this time the 3.0 network. Alright, so 172.16.3. Alright, .0. Okay, so you might be confused, no? I already declared 172.16.3.0 network on R1. Okay, why am I declaring it again on R2? So simply the answer is that is because if you're going to look at R2, you're going to the basic principle is to declare all directly connected networks. So in this case, okay, if you're going to look at the network from R2's router 2's perspective, okay, and count the number of directly connected networks, 170.16.3.0 is also included on its list. Okay, so you need to declare it as well. Alright, so it doesn't mean that you declare it on R1, and you don't need to declare it on R2. Okay, as long as it is directly connected, that is our basic principle of network advertisement. So you need to include it as well. So the subnet mask, again, /30, that is 000.3, opposite of 252. Alright, then as you can see, no, right there, since this line right here is the line that is being used by R1 and R2 to interchange, right, or to update routing table. So this line is being used by R1 and R2 to exchange hello packets. So right then and then, no, once I entered the correct network values, okay, you notice, no, there is a message that tells me that the network adjacency between these EIGRP neighbors or neighbor adjacency has been established. Okay, so that is one indication that you are doing the correct configuration. Okay, but it doesn't end there. You still have one more network to declare. That is the 192.168.10.8 network on the other side. So I'm gonna put that on my list as well. 192.168.10.8. Alright, the wildcard mask /30, so that is 000.3 as well. Enter. Okay, so we have these three declared networks on R2. So we're done with R1, we're done with R2. Okay, so the last router that we're going to configure is R3. Okay, the last router that needed setup for EIGRP. Okay, so let's proceed with that right now. Okay, so same process, just go to global mode, okay, router EIGRP autonomous system 1. Okay, make sure that you're using the same AS number, or else you will have problem with EIGRP communication or updates. Then, okay, let's try and configure also EIGRP router ID on this router. We're gonna name it just to apply what we discussed from previous slide. So we're gonna use 3.3.3 here. Okay, and then we're gonna start declaring networks. So I'm gonna declare the first one, 192.168.10.8, the one on top that is directly connected to R3. So that is 000.3, y.3, because the subnet mask is /30, so that is 252. Okay, enter. So again, no, as you can see, same thing happened when we configured this link right here between R1 and R2. So when we make R2 and R3 link active, okay, you noticed that we receive a neighbor adjacency turn on as well. Okay, so next we're gonna start off, or we're gonna continue declaring networks. This time the 10.4, that 10.4 network, okay, 000.3. So I'm just gonna go faster here. Alright, and then the last, okay, so this one, it also gave me a message for neighbor adjacency on which particular router. Again, R1 and R3. This one right here. That is the neighbor adjacency that was established. Okay, so the last network address, network 192.168.1.0.000.255. Okay, why 255? Because it has /24 subnet. Okay, do not be confused again with that. No? If you need calculation before you do this one, if you're still not familiar with the or you're still confused, no, with the invert values, okay, just make sure that you're typing the correct subnet mask or the wildcard mask value. Okay, so you can use scribbles, you can use notepad if you want, or any scratch paper to compute for that. Okay, and then we're just gonna press enter here. All right. So by the way, let's say for example, let's say yeah, you committed mistake. All right. So instead of typing 255 here, okay, you made a mistake. Okay, you accidentally put .3, okay, which is an incorrect wildcard mask. So how are we going to correct it? Okay, all you have to do is to remove first the invalid entry. Okay, so using the command no network, or you can just go back to the previous command by pressing the up arrow key on your keyboard. Okay, up arrow key will give you the previous entries that you've entered, okay, in Packet Tracer. Or if you want, you can just type it in. Okay, so all you have to do is to follow whatever you've written previously. So no network, for example, I'm going to remove this one. So I'm just going to type in no network 192.168.1.0 along with the incorrect wildcard mask. So 00.255. Alright. So when you do that, it will remove this entry on its network declaration. Alright. And then all you have to do is to type it again. So type the entry back again. Okay. This time with the correct subnet mask or wildcard mask value. Okay, so you can do this one, or you can do this procedure, no network. All you have to do is to put no at the beginning of each command line that you enter, and then don't forget to re-enter back the correct values. All right, so network right there. Okay, so that's it, for step procedure number 2. All right, so moving on to our next task. All right, this time we're gonna configure passive interfaces. So after configuration of the EIGRP along with the autonomous system member, okay, after you're done advertising directly connected networks, so the next task is for us to configure passive interfaces. Now, what exactly are passive interfaces? All right, so during EIGRP routing updates, it may be necessary or actually advantageous to include the directly connected network in the EIGRP routing table. But at the same time, we do not allow any neighbor adjacencies of that interface to form. So for example, let's say we all know that the link that is being used by R1 and R2 to exchange routing information is this link right here, right? The link that is used by R2 and R3 to exchange routing update is the link right here. So the one link in between. So as you can see right here. So this is the main links wherein routers are using to exchange routing information update and form adjacencies with each other. Okay? Now, whenever you run EIGRP, okay, routers behave this way. So all of the active ports are given routing updates. So it means that even the LAN that is connected to this router, since it is an active port, okay, EIGRP routing update will still be sent across this network right here, across this link. But as you can see, there's no router connected to R1. Okay, this is actually the connection going inside your local area network. So there will be no device that will make use of that particular update. Okay, and there's no device here on this particular LAN that can form EIGRP adjacent neighbor with R1. Okay, so we're just wasting resources. R1 is just wasting resources to continuously send routing information on this port right here. Same with this scenario on top. Same with this LAN connection here on R3. So in that case, passive interface is being configured or are needed to be configured on those interfaces to stop routers from sending any EIGRP routing update out of that particular interface. Okay, so there are two primary reasons for enabling passive interface command. So I mentioned number one a while ago, that is to suppress unnecessary traffic, okay, such as particularly LAN interfaces. Okay, so we are suppressing the unnecessary update traffic created by the EIGRP uh, adjacency, okay, packet to go out of this LAN. Alright, because there's no routers connected. Okay, and there's no need for that update on this particular port. Okay, the other one is to increase security protocols. Okay, so when you prevent routing updates to go or to be distributed from this port, okay, you are preventing unknown rogue routing devices to receive EIGRP updates, okay, from this LAN right here. So to declare these ports as passive interfaces, all we have to do is go back to our EIGRP configuration mode. Okay, so I'm just gonna do that right now. So I'm just gonna enter R1. Okay, all right. So enable. Okay, global mode, and then I'm gonna go back to router EIGRP, autonomous system 1. Oh, sorry, router EIGRP 1. All right, and then I'm just gonna declare this port right here as passive interface. So you need to be sure, okay, what particular port is this interface that is facing your LAN, because you will need to declare that inside router EIGRP as passive interface. So for example, if this is G00, that is gigabit ethernet 0/0, okay, let's just take a quick look on that using show IP interface BR. So that one right there. So this one is the port that is being used for the LAN link. So that is G00. So I'm just going to declare it as passive, okay, using the command passive interface G0/0. Okay. So again, no, if you commit mistakes declaring passive interface, let's say you put it 1, for example, all you have to do is to go back to that command using up arrow key on your keyboard and then type in no in the beginning. All right, so no passive interface will remove that particular selection, okay, from being passive. All right. So by the way, I haven't shown you a command, okay, to check, okay, and review if a certain networks, okay, the one that we declared a while ago, are accepted by the router. So to do that, okay, all you have to do is to run okay, show IP protocols. Okay, so show IP protocols will give you the following information. So as you can see right there, okay, it will show you the autonomous system number 1, AS number 1. It will also show you the router ID. Okay. You also have, okay, this one right here are the ones that we've declared a while ago. Okay, routing for the following network. So all you have to do is to cross-check, okay, if those networks are correctly declared. So 1.0 network is this one right here, the LAN link. 10.4 network /30 is the one on this link right here. 3.0 16 is the one on the middle. So as you can see, no, since we used the correct wildcard mask value, so it was evident here, as you can see, no, we have the exact matching subnet mask as to the given topology, and of course, we also have the passive interface on this link, the one that we declared a while ago. Okay, so we're done with R1. Okay, declaring networks and naming the passive interface. Let's move on with R2. So we're just gonna follow the same procedure for R2. Okay, so just enter R2. All right, and then okay, so privilege mode, global configuration mode, or let's check first again using show IP protocols. Okay, router ID, we declared that a while ago. Okay, autonomous system number is 1. So we have that as well. Okay, routing for the following networks. Okay, so let's just review that very quickly. So 2.0, we have that. 3.0/30, the one in the middle. And then 10.8/30, the one that is connected on R3. Okay, so we haven't declared any passive interface here yet. So we're just going to do just that. All you have to do first is to find out what interface ID is connected to the R2 LAN. So to do that, again, we have show IP interface VR, so we can just check it which port is being used by that IP address. So that is, I think that is 0/0 as well. So let's go back to our router EIGRP global mode, router EIGRP 1, and then we declare passive interface inside that router G0/0 as well. Okay, so enter. So we have that already. Okay, let's just close this one and then proceed with R3. So we're just gonna inspect the EIGRP declaration here along with the network address that we declared a while ago, if it has matching network address with our topology. Okay, using the command show IP protocols. Alright, so we have AS number 1, we have router ID 3.3.3.3. Okay, we also have network declarations. We have 10.8, okay, the one in the middle. We have 10.4, the one with R1 connection. And then we have the 1.0 network, okay, the one with the LAN. That is our LAN right there. Okay, so we have all of these values. Okay, so all you have to do now is to declare passive interface. So again, to check which port is being used for LAN, I'm just going to use this command right here, and then just look at the IP address that is being used on that particular port. So since 0/1 is not used, so obviously it is G again 0/0. So I'm gonna go back, global mode, router EIGRP 1. Okay, don't forget the AS number 1. And then we're just gonna declare passive interface G0/0 on this command line. So enter. Alright, so yeah, that's it. So we have successfully configured passive interfaces. Let's just make this one smaller. Okay, on all of the 3 routers. Okay, so we are on this part right here. Okay, for a while. Okay, so we are already finished with task number 1, 2, and 3. Okay, so this time the next task is to disable automatic summarization. Okay, so let's talk about that first very briefly. Okay, so moving on, another way to inspect if your network adjacencies are working pretty well with this router, since we already declared and are already activated router EIGRP with AS number 1. So one way to find out if they are establishing network adjacency with their neighbors is to use another show command. Okay, so for example, let's say I'm gonna go to R1. Okay, the show command that we're gonna use is the show IP EIGRP neighbors. Okay, so take note of the command. So we have the show IP EIGRP neighbors. Alright, so it is being issued inside privilege mode. Okay, so once you've entered this command, okay, when you press enter right here, so just show that to you. Okay, it will show you, I'm currently at R1 right now. So it will show you the neighbor adjacencies that is being formed across routers or across neighbor routers of R1. So in this case, okay, that neighbor adjacency is R1 to R2 and R1 to R3. That's why you see two entries here. Okay, so it has a neighbor adjacency with 172.16.3.2 address or 3.2 interface using S00 interface. So that is one right here. Okay, that is the interface of R2. Because if you're gonna check the R2, let's go back. Show IP interface brief. Okay, so you will see that property of R2 right there. So this is the S003.2 address, okay, which is part of the R2 interface. Alright, so let me just go back. So that is the first neighbor adjacency from R1. Okay, the other one is on the side. Okay, the 10.6 network. Okay, so this one is the 10.6. Alright, the interface on R3. Okay, this one right here is the 10.5. Okay, the interface on R1. So if you notice, okay, we have two neighbor adjacencies. This one right here is the 11 and the 13 are the values for the seconds that remains before declaring neighbor down, or the maximum hold time timer, okay, whenever a hello packet is received. All right, so we mentioned a while ago that in order for them to establish adjacency from each other, they are sending hello packets as part of their negotiation process. So that this one right here are the counters for that. We also have the uptime value. Okay, and then of course the interface that are that this IP addresses are linked or located on a particular neighbor. So this is the neighbor for R1. Okay, this is R1. Let's try and check R2. Okay, using the same command, show IP EIGRP neighbors. So R2 neighboring router going to R1 and then going to R3, facing R1 and R3. That's why you also have two entries right there. Okay, so it means that your neighboring EIGRP adjacencies are functioning well. Next, of course, we cannot to the ultimate test. Okay, whenever you wanted to see if the dynamic routing is working well, is the end-to-end connectivity. No, the process that we're doing here is just checking if the neighbor adjacencies between routers are properly accepted or active. So show IP EIGRP neighbors. So that one right there. So you also have two active neighbors. Just in case you're only seeing one, okay, on this list. Okay, so that is the time that you need to troubleshoot and then try to check for some errors, because as you can see, no, you should be seeing at least two neighbor adjacencies since we have 3 routers set up like this one. But of course, it depends on the network topology. No, you might have one neighbor adjacency, 2 or more than 3. So it still depends on the physical layout of your network. So if you're looking at your topology that should have 2 neighbor adjacencies, okay, when you check on the CLI, okay, to verify that, you should also be seeing 2 and 3s. Okay, so if not, okay, for example, let's say you only see 1, then that is the time that you will need to check or recheck your probably the neighbor or the network declaration that you did had some errors to it. No? So you need to troubleshoot. Okay, so that one right there. Okay, so the next useful show commands that you should be aware of, aside from the show IP EIGRP neighbor, is the most useful show IP route command. Okay, so we've been using this command since we've learned how to do static routing as well as the router RIP, RIP version 1 and 2. Okay, so the show IP route command is another way to verify that EIGRP and other functions of the router are configured properly. Okay, particularly in examining the IPv4 routing tables. Okay, so let's see the routing entry of R1. Now using show IP route command, and then we're going to explain the entries. Okay, so look at this. Now, when you do show IP route command, okay, you will have the following codes on top that will let you know what are the labels or the criteria that are being shown. Okay, the first letters right there are the ones that are shown in the leftmost corner of the results. All right, so they have the following legend. L stands for local, that is the local link. C is for directly connected. S is for static route. R is the indicator that you're using RIP as a dynamic routing protocol. For EIGRP, we use D, that one right there. So since we're focused on EIGRP, we're going to look at entries D. Okay, D stands for dual algorithm. All right, and then the next protocol that we will be using in the next chapters is O, which stands for OSPF. So let's focus now on D first. Okay, now looking at the topology, guys. Look at this. Now, how many entries of these do we have? So we have this one right here, 1. We also have this one right here. Okay, let me just zoom in on that. So we have this first entry. All right, 1. We have this one, 2. And we have this one, 3. Now, take note of the network addresses. This is 16.20, 16.10, 16.10.8. So we are currently on R1. This entry is right here that was added on this routing table with the letter D label or code means that these are the remote network that was learned, all right, via EIGRP. So this was the update that was given to R1 so that R1 could map or receives a map, something like a map, okay, or an update so that it can reach the following networks. So whenever there is an entry, no, on its routing table that says, okay, I know how to go to that particular network. I know how to go to this network. All right. And I learned it via EIGRP. Okay. So you have the following entries here. So it means that this router can now go or reach those remote networks. So we have in total, we have 3. Now, if we're going to visually check that, okay, where's the location of those networks that was added on the routing table of R1? Okay, so basically, we have 3 directly connected networks. If we're going to count the number of remote networks from R1, the one that are directly connected to it, okay, we have this network right here, 1, This one right here, 2, and this one right here, right? So that is the 16.20 network, 168.10.8 network, 168.1.0 network. So those are the 3 remote networks that are not directly connected to R1. So how can R1 learn how to go or how to reach those networks? Okay, so that is the purpose of the EIGRP that we are configuring a while ago. Alright, so they are now exchanging routing information, and each of the entries that was declared on the router inside the EIGRP are now being advertised, alright, on all 3 routers. Okay, that's the reason why if you're going to look at the labels, they are starting with letter T. So let's take a look at that. So we have 2.0 network. That is the one that is on this entry right here. Alright, see that? Okay, this one right here is the 1.0 network. This one right here. Okay, so very clear, no? You have the other one, remote network. The third one is the 10.8. So that is the other entry right there. So as you can see, no, all of the remote networks are now saved on the routing table of R1. Okay, it's complete, no? There's no remote network missing on the list. Okay, so it means that R1 and then the neighbor adjacencies, their exchange of routing information, okay, in terms of the EIGRP that we've configured a while ago is working pretty well. Okay, take note of that, no? Now, just in case, no, you expect 3 remote networks to be part of the routing table of R1. But just in case you only see 2, for example, you only see 2 letter Ds, okay? There's one route missing, or there's one remote network missing. That is the time that you will need to troubleshoot it. Then try to look first at the IP addresses. Okay, try to look if the network declaration on other routers are correct. And then also try to check for the subnet mask or the wildcard mask value. Okay, that was declared inside EIGRP. I think that is part of the troubleshooting practice. Okay, one of the packet tracer that you're going to submit is a troubleshooting wherein you will try and check the error that is causing the problem. Why, for example, R1 is not receiving an update. Okay, of course, the other reason is that okay, you should make sure that the interfaces are working pretty well. So you should be seeing greens. Okay, IP address are all good. Subnet mask declarations are all good. Okay, you should not be seeing any red indicator lights, especially on these links right here, the one in the middle of the routers, because these lines in the middle, the one links, are the ones being used by router to exchange routing updates. Okay, and of course, just make sure that they are not declared as passive. Okay, you don't declare these lines passive because, of course, we all know what passive interface does to the EIGRP operation. Okay, so we only declare passive interface on the link that goes to your LAN. Okay, so this one right here. So you need also to check for that declaration just in case. Alright, so this is the routing table of R1. So we have it all good. Okay, so to check on other routers, so we're just gonna do the same procedure. Enable, right? Show IP interface, very useful. Show IP route, very useful command. Okay, so how many remote networks do we expect R2 list has? So we have the same with R1. So we have 3 directly connected. Okay, the remote networks are this network 1.0, 10.4, and 16.10. So checking them on the routing table of R1, you should see 3 letter Ds as well. 1, 2, and 3. Alright, so R2 is good, up and running. R3, show IP route. Alright, so let's see. So for R3, okay, so we have 1, 2, and 3. Okay, I enabled disabled the no auto summary a while ago. That's why this one detected another network. But as you can see, no, it is declared null already because I put it back to network summarization. So we're gonna talk about network summarization a while ago. Oh, sorry, in a while. No, we're gonna talk about that in the next few slides. Okay, but just in case, if you're going to look at R3's routing table, it's just the same. So we're all good with this one as well. So basically, if you're going to look at the summary of network directly connected and remote networks, so all of the routers has 3 directly connected, okay, and 3 remote networks. So if you're going to observe the routing table, okay, of each router that are running EIGRP, you should be seeing at least 3 letter Ds, okay, 3 Ds, okay, per router. Okay, so moving on with the fourth task. Okay, so it says disable automatic summarization. Alright. Now, since this topology contains discontiguous network, so therefore, we need to disable automatic summarization on each router. Okay, so it's just pretty straightforward config, no, on how to disable the automatic summarization. Okay, so to do that, all we have to do is to go back to our routers. Okay, enable config T. Okay, we're gonna go back to router EIGRP1 and just issue the command no auto summary. Alright, so no auto summary. So this one right there. So no auto summary, we'll disable auto summarization feature, okay, of EIGRP routing protocol. Since it has tendency not to summarize routes to their classful networks automatically, so we don't want that. Alright, we don't want that. Okay, it actually reduces the amount of routing information on the routing table, but it's still better if we disable auto summarization so that networks can be advertised as it is. So whatever you declare network, especially in a discontiguous network, can be advertised as is. Okay, that's why we disable the auto summary feature. Okay, so that's what we do here in R1. Let's move on with R2. So just copy the same procedure. Global mode. Alright, router EIGRP1, no auto summary. Enter. Close. I'm gonna go to R3. Okay, global mode. Okay, router EIGRP1, no auto summary. Alright, so that one right there. So we disable the auto summary feature to release all this contiguous network from being auto summarized by EIGRP, going back to their original classful network subnets. So we got rid of that. So the next thing that you need to do is to save, and the last one is to verify end-to-end connectivity, which means if we are sure that it is already a converged network, we're gonna test by sending ping from different PCs. So first we're gonna save the configuration to finalize it. Okay, go back to privilege mode. I'm gonna type in copy run start to save. That is on R1. R1. So let me do that the same procedure with R2. Alright, copy, run start. Okay, enter. So that is saving the configuration. R3, copy, run, start, enter. Alright, so after we save the configuration, so we finalized everything on each router, it's now time for the ultimate test, okay, to complete this topology. So we're gonna try and verify. By the way, number 6 task, examining neighbor adjacency, is the one that we did a while ago when we type in the command show IP EIGRP neighbors. Okay, so just to check, and also the show IP route command. Okay, to check if you have properly configured the parameters inside EIGRP. Next, the last ultimate test is to verify end-to-end connectivity. So we're gonna try and ping now routers or computers, no, from different networks. So I'm just gonna go ahead and start off with PC1, okay, and I'm gonna try and ping PC3. So I'm just gonna check its IP address, that is 1.10. PC3 is 1.10. So I'm coming in from PC1. So I'm gonna type in ping 192.168.1.10. So I'm actually pinging PC3. So let's check if our network has been converged. Okay, so the first RTO is just acceptable since this will be our first ping. But if you try to repeat the process again, you can see that we have 100% reliable communication. Okay, send and receive. Okay, what about, okay, I'm gonna ping PC2. Let's check on the IP address. That is 2.10. I'm still at PC1. Ping 172.16.2.10. Okay, so I'm pinging computers from PC1 to PC2. Alright, first RTO is acceptable. Just going to repeat the process. Alright, so successful 100% rate. Okay, so if you try to ping, let's say for example, I'm coming in from PC3 and then I'm going to try and ping PC2 as well. 16 that the IP address of PC2 again. That is 2.10. Okay, so it still had a successful connection. Alright, so it means, okay, we already have a converged network, okay, running EIGRP, okay, all of these computers can be able to reach the other remote networks, alright, with ease and no issues, okay. That is because we've successfully configured dynamic routing protocol using EIGRP on these routers. So we already have a converged, what we call as a converged network. Alright, so yeah, so this is EIGRP implementation on IPv4. We're gonna have the final topology for EIGRP, but this time we're gonna do IPv6. Okay, so that will be on the next slide. Okay, now for IPv6 network, let's just make this quick. Since we already discussed the basic principles of EIGRP parameters commands in IPv4 a while ago, so when you apply it in IPv6, just pretty straightforward. Okay, all of the commands are mostly identical. Okay, all of the principles are identical, so we're not going to go through them. We're just going to go straight with the uh, implementation of EIGRP on an IPv6 network. Okay, the only difference is from IP command, okay, we're just gonna add v6, alright, on every command that is applicable in IPv4. So for example, if you're going to apply let's say router EIGRP command in IPv6, alright, so it's gonna be IPv6 router space EIGRP space the autonomous system number. Okay, so let's try to apply that in this given topology. So we have the same 3 router setup. So 3 directly connected networks, 3 remote networks, IPv6 networks that is. So we're gonna try and configure IPv6, EIGRP IPv6 version here. Okay, using this dummy topology. Okay, so all the networks are already given right there, and I believe the IP addresses are also pre-configured as well, so you don't need to worry about the interfaces. So to check on that, you have to show IPv6, alright, interface ER. So as you can see right here, so we already have IP addresses working on interfaces. So we don't need to configure them anymore. So just go straight forward with the EIGRP implementation. Okay, now enable for you to apply EIGRP implementation with this topology, okay, IPv6 network topology. Okay, the first thing you need to do is to enable IPv6 unicast routing. Okay, so we are doing that, okay, with most of the routing tasks that we did from the past modules. So whether it is static or dynamic, like using grep or ripv2, okay, whenever we are inside IPv6 network topology, you need to enable that first. So we're gonna do that on each router. So I'm gonna start off with R1 global mode. Okay, and then issue the command IPv6 unicast routing to enable unicast routing within routers. So we're gonna do this one. Same with R2. Okay, so we issue it inside global mode. Routing. Okay, close. Proceed with R3. Same command. Global mode IPv6 unicast routing. Okay, so we have that configured already on 3 routers. The next thing we need to do is to enable IPv6 routing process using EIGRP. Okay, we're gonna use the same autonomous system number 1. Okay, so the next steps, we're gonna enable the EIGRP process on all routers and use 1 as the autonomous system number. Okay, so this is the process in terms of IPv6 version. Okay, so we have, just closing on that. Okay, the command will be IPv6 router EIGRP and then autonomous system number 1. Alright, so take note, no? In IPv4, we only configure router space EIGRP space AS number. But this time, it will start off with IPv6 router EIGRP autonomous system number. Okay, so that is the syntax. Enter. And then this time we're going to issue no shutdown just to make sure that you have a live EIGRP configuration. Okay, or to turn on the EIGRP if not yet turned on. Okay, so we move on with our 2. Okay, do the same config. So we have IPv6, okay, router, EIGRP, autonomous system number 1, and then no shutdown. Okay, go to R3, do the same process. So we have IPv6 router, okay, EIGRP, autonomous system number 1, and no shutdown. Alright, so yeah, that's it. So we have 1, 2, 3 already configured routers running EIGRP, autonomous system number 1. Okay, this time, the next procedure, same with IPv4, we declared, let's say, what's missing? Yeah, router ID. Alright, so let's have the router ID for each of these routers. So we're just going to follow the same format. Okay, even though it's IPv6, now we're going to use an IPv4 format for router ID. So we are still inside the router EIGRP, don't forget. So all you have to do is to issue the command EIGRP, okay, and then router ID. Okay, for R1, we're going to use 1.1.1. Okay, move to R2. Okay, EIGRP router ID 2.2.2. Okay, for R3, we're gonna do EIGRP router ID 3.3. Net3. Okay, so those are the commands. So it's just pretty straightforward again, no? Even though we're using this network topology is IPv6, our router ID is still on an IPv4 format. So just be aware of that. So enter. I'm gonna close this. Alright. So we are good with the router IDs. Router EIGRP version 6 is running on all routers. So the next thing we need to do is what? Okay, if you guessed, declaring networks. Alright, declaring networks, directly connected networks, the one that we did a while ago with IPv4, right? So we declared the networks that are directly connected on each router using the command network space network address space wildcard mask. Alright, so that is the next, actually that is the next procedure, okay? We're gonna declare networks, but this time, this is the part that actually is a bit different when it comes with IP version 6. Okay, a bit different, but a bit easy or easier in terms of configuration, because you don't need to worry about typing the complex network addresses to declare on each router. Okay, all you have to do is to enable EIGRP for IPv6 on each interface, alright, on each active interface. Okay, take note of that. So you're just going to enable and call IPv6 EIGRP along with the autonomous system number that you are being used, and then enable that inside the active interface without typing any of the network addresses and without computing, of course, the wildcard mask, because IPv6 doesn't have wildcard bits. Okay, so to do that, okay, let's just go ahead and do that in R1. Just show that to you. Okay, so first we need to find out how many active interface does R1 have. So as you can see in this topology, now we have 3 active topologies it shows in the topology. So we just have to find out the interface IDs of this topology so that we can enable EIGRP IPv6 interface or IPv6 EIGRP inside those active interfaces. So to do that, I'm just gonna type into show IP interface brief, and then just take a look at the active interfaces. Okay, the one that has, oh sorry, it's not IPv4, so I'm just gonna retype that. Do show IPv6 interface brief. I typed IP a while ago, so that's why it showed an IP address, IPv4 address. Okay, so this time we're gonna have, it shows the active IPv6 address. So we have the following. So the one that are shown up and up are the active interface, and the one that has IP address. Okay, so it has G00, we have S00, and then we have S001. Okay, so we just have to take that into our list. Okay, exit our config router, go back to global mode. Okay, go back to global mode, and then all we have to do is to enter each one of those active interfaces. So I'm gonna start off with G00. Okay, and then inside I'm just gonna declare IPv6 EIGRP and then autonomous system number 1. That's it. So you are adding this interface, this active interface, to be part of the IPv6 EIGRP dynamic routing update. Okay, so since R1 has 3 active interfaces, okay, so we're done with the G00, so we're gonna enable also IPv6 EIGRP on the other active interfaces. So I'm just gonna have to switch interface. So you don't need to exit anymore. So just type in interface S000, the one that we saw a while ago, that is active right there. And then just type in again IPv6 EIGRP1, enter, change interface to 1. I'm using my up arrow key for easy typing. And then IPv6 EIGRP address number, AS number 1. Okay, so all you have to do again, is to declare this command inside all active interfaces. So make sure that you are using the same autonomous system number for active interface. Okay, so we're done with R1. Okay, so we're good with R1. So I'm just gonna go ahead and exit. Okay, and then proceed with R2. So I'm just gonna follow the same procedure. Okay, I'm gonna show IPv6 interface brief to look at the active interfaces. So I think we have the same. We have G00, we have S00, and then we have S001. Okay, we also have one loop back here, but I guess we're not going to use that for now. So we have those 3 active interfaces. So again, go back to global mode. Okay, so interface, we're gonna start off with G00. Okay, IPv6. Alright, EIGRP autonomous system number 1. Okay, I'm gonna go to S00, type in the same command as you can see right there, the pop-up message saying that a certain adjacent neighbor has been found. Okay, automatically shown. Same procedure or same event that happened with our before a while ago. Okay, so I'm just going to continue on with the other 4 and then declare autonomous system number 1 right there. Okay, so that completes R2. Let's move on with R3. Okay, so for R3, show IPv6 interface BR to check on the active interfaces. So we have the same values. We have G00, S00 or up, and S001. So just gonna mind that those interfaces. So interface G00 and then IPv6 EIGRP1. Alright, switch with S000 EIGRP1. Okay, so you expect another pop-up message establishing network link from R2 going to R3 or adjacent neighbor link. Okay, and then the last one is this one. So when I add this on the list, I'm going to expect another adjacent bridge that will be established between R3 and R1. So take note of that. Look at this. So enter that one right there. Okay, new adjacency to R1. Okay, the neighbor router on this side. Alright, so yeah. Okay, I guess we're done. Okay, now to check for IPv6 network adjacencies. Okay, you can have the summary of the show commands on the NetAcad portal. I think we uploaded a list there. Okay, for the easy summary of the different show commands. Or if you want, since you've been listening since the start of this module, then you might as well have a list on your own. Okay, so to check for adjacencies, we have show IPv6. Okay, EIGRP neighbors. Okay, notice the difference. In IPv4, it's only show IP EIGRP neighbors. This time it has v6. So when you press enter, you're gonna receive the same adjacent neighbor list which is 2. Okay, the same with our IPv4 topology a while ago. Okay, so it's just the same. Okay, I'm gonna go ahead and check on R1. Show IPv6 EIGRP neighbors. Alright, again, you also have 2. Alright, for R2, show IPv6 EIGRP neighbors. You also have 2. Okay, so it means that the neighbor adjacencies on each of these routers are working well. Okay, so again, to check for the parameters when it comes to the configured parameter for each router, use the command show IPv6 protocols. Again, notice the difference with the command. You just zoom that in. So in IPv4, it's only show IP protocols. This time it's show IPv6 protocols. So you will have the same output. Okay, almost the same output right there. Okay, so you have interfaces. This time it's not networks. Okay, it's interfaces. Okay, the one that is declared inside EIGRP AS1. So you have, yeah, this one right there. So just a minimal content as compared with the IPv4 a while ago. Okay. All right. So next, just the same with IPv4. It is better if we suppress the routing update information updates on LANs. So that is using passive interface, right? So just the same with V6, okay, you need also to declare passive interfaces on all LAN links. Okay, so for the advantages that we mentioned a while ago, it's just the same with V4. Okay, so to do that, okay, let me just zoom in. For R1, I'm just gonna do R1. Okay, global mode. All right, and then we have IPv6 router EIGRP autonomous system 1. Go back on that interface. Okay, and then inside this interface, you declare, for example, let's say passive interface. We're going to declare G00 as our passive interface. So to suppress update going out this interface ID right here. Okay, because switch doesn't need that. Okay, and it's more vulnerable to security risk. So we don't want that to happen. So we're cutting the update on this LAN link right here. That's why we're declaring passive interface. As we discussed with before a while ago, same advantage with V6. Okay, so we have that. Okay, so next we move on with R2. So just follow the same procedure, global. All right, so IPv6 router EIGRP1, and then declare passive interface G00. Just make sure that you are targeting the correct interface. So since I know that this is already G00, so I didn't check already. No? So, alright, so we have R2. For R3, just follow the same procedure, global mode. IPv6 router EIGRP1. I'm going to declare passive G00. Alright, so yeah. So the last thing that we need to do is to test for connectivity. So I'm just going to check for IP configuration of this one. So I'm just going to try and ping PC3. Alright, so I'm just going to copy this address. And then I'm going to use PC1 to ping that. So I'm going to try and ping this address right here. Okay, check if we have convergence. Okay, so PC1 and PC3 successful. Let me just go ahead and check PC2. Copy. I'm gonna paste that on the ping test here. Alright, enter. Okay, then we also have the same convergence. Alright, so yeah, I guess that's how we achieve convergence with IPv6. So you notice not only minimal differences in terms of the commands. Just do not be confused yourselves whenever you try to apply V6 configuration and V4 configuration along with the differential commands. Okay, the only major difference is in terms of declaring the network addresses. So in V4, you declare it using the network address and then the wildcard mask. In V6, you don't need to call or to type in the exact network addresses. All you have to do is to enable IPv6 EIGRP inside the interfaces. Alright, so yeah, I guess that ends. Let me just show the summary slide. Alright, so I guess that ends module 5. Okay, and apologies if it took a few hours or I think more than an hour for this video. I guess you can just skip to the most recent or the most important one or the one that you did not understand. Okay, in terms of the comprehensive discussion. Okay, so again, thank you so much for listening. Hoping for a productive week number 5. So almost done with this SAMS module. Okay, the last module will cover OSPF. Okay, single area and multi-area. Alright, take care guys. Okay, send me questions or queries whenever you have something in mind. Okay, thank you so much.